First of all, I'd like to start by sharing the abstract of our study. Our study focuses on improving scoliosis braces by applying principles of statics and mechanics of materials. These braces work using a three-point pressure system to realign the spine, and we explored how personalized designs and advanced modeling like finite element analysis can make them more effective and comfortable. We looked at stress distribution, identified key load-bearing areas, and proposed ways to refine materials and force application. The goal is to create braces that adapt to individual needs, improving outcomes while making them easier to wear. And this research brings us closer to better, more patient-friendly solutions for scoliosis treatment.
Scoliosis is the abnormal curvature or twisting of the spine. It can affect people of all ages, from infants to adults. Scoliosis brace is used to overcome this problem. Scoliosis brace is a device worn around the torso that can help prevent the curve from getting worse. It can also make it less likely that you will need surgery in the future after bone growth has stopped. Static and mechanics of material are crucial elements that need to be considered whenever one wants to create or build a biomedical device so that the device can operate properly. Also, the static and mechanics of material are used to analyze and design structures such as bridges, building, and machinery, ensuring that they can withstand the loads and forces that they will subjected to in their intended use. Statics is the study of the forces that act on subjects that are at rest or in equilibrium. It focuses on how forces are distributed within a system, and this is crucial for designing stable structures. Meanwhile, mechanics of materials studies how different materials deform under some applied forces. It determines the internal forces, stresses, and strains within a structure, which is important to ensure the safety of the user. In the study of statics, we can draw a free body diagram to visualize the forces exhibited on the brace. This helps in determining forces effectively across the brace to achieve the desired corrective effect without causing discomfort for the user. The brace must apply the correct force to the spine while maintaining stability so that the spine can be fixed correctly. From mechanics of material perspective, stress and strain used in this case of study, we can see different materials exhibiting various stress-strain behaviors, which influence how effectively a brace can provide support. Basically, stress is defined as force per unit area within a material when subjected to external loads. Strain is defined as the deformation experienced by a material when subjected to stress. This report aims to demonstrate statics and mechanics of material using real-life example. LO1 use free body diagram to perform an equilibrium-based analysis for various structure. LO2 evaluate stress and strain of the biomedical device.
Scoliosis is a condition defined by a sideways curvature of the spine, most commonly seen in adolescents. While mild cases may not seem concerning, untreated scoliosis can worsen over time, potentially leading to severe complications. As the spinal curvature progresses, it can significantly reduce chest wall compliance, making breathing more difficult. Increased work for the lung at rest during exercise and even during sleeping are common challenges for patients with an advanced scoliosis. To prevent this progression, doctors often recommend scoliosis braces, which are a key non-surgical treatment option during a patient growth phase. One significant study has been made to examine the effectiveness of spine cord brace in treating adolescent idiopathic scoliosis. Among 639 patients treated, the study found that 74.2% achieved successful treatment outcomes, showing the potential of bracing as a reliable intervention. Braces like the spine cord brace work by applying corrective pressure to the body, targeting abnormal spinal curve. Ideally, the brace is worn up to 23 hours a day until skeletal maturity is reached. This constant pressure counteracts the progression of spinal curvature while elevating stress on fatigue muscle. Braces also utilize the principle of the three-point pressure system. This method applies targeted forces to the spine, counteracting the lateral curve and promoting spinal alignment. The system also encourages derotation, a key aspect of correction. While braces are effective, they come with challenges. Patients may experience discomfort in the spine, rib cage, and buttocks, making adherence to wearing schedule difficult. However, the effectiveness of bracing depends heavily on how consistently it is worn. In summary, scoliosis braces are vital tools in managing spinal curvature during growth. They work by applying corrective pressure, leveraging biomedical principles, and preventing further progression. By wearing the brace as prescribed, patients can avoid severe complications and improve their quality of life. That's all from me. Thank you.
Designed for the non-invasive treatment of scoliosis, the Boston Spinal Bracing System is particularly effective for spinal curves with apexes between the 6th thoracic and 3rd lumbar vertebrae. Uniquely, the top of this brace is designed to be flexible and sit under the patient's armpit to provide stability and minimize movement. This picture shows that two forces labeled F1 and R1 exert pressure on the ribs to influence the spine, while a third force, R2, acts on the pelvis. Force F1 serves as the primary corrective element, while force R1 and R2 provide counterbalancing support. In this work, the brace uses a simpler three-point force mechanism for a case of left lumbar scoliosis. The variant of corrective forces used can also be effective for additional lower right thoracic scoliosis, despite the lack of force applied to the axillary extension. This arrangement of forces corresponds to the Boston thoracolumbar brace variant according to the reference manual. The three applied forces are crucial in the correction of the lumbar curvature, while the other parts of the corsets have auxiliary function. The three-force design is statically determinable system that allow distribution of forces to be unambiguously determined in the both experimental study and numerical analysis. In this case, this picture was using the same triad of forces to support R1 and R2 along with a preload force F1. Two fixed support were established and initial load was applied. In addition, the gravitational force G was included in the model for a more complete representation. An additional F2 was then introduced to match the conditions of experimental tests using an electronic speckle pattern interferometer ESPI system. This optical interferometry system measured the displacement along the z-axis of the computer model. The introduction of this smaller force was strategically planned to allow the measurement of small displacement within the interferometer's range while maintaining the linear elastic range of the material. The final simulation output, which calculated the shell displacement differences before and after the introduction of force F2, was then processed for further investigation. Polypropylene with a modulus of 1500 megapascal and a Poisson ratio of 0.3 was selected as the shell material for the orthosis because of its non-durability and flexibility, making it well suited to achieving the desired balance between stiffness and flexibility. A 10-knot tetrahedral element was used to construct the FEM model. This element type is particularly advantageous for accurately representing complex 3D geometries and provide excellent numerical performance for simulating the elastic behavior of materials. An iterative process of mesh refinement was performed until the von Mises stresses variation was less than 5% with increasing knot density. In addition to determining the distribution of von Mises stresses, the study also identified the field of principal stresses in the orthotic shell, represented graphically by a system of vectors for each shell element. The dense array of principal stress vectors allowed for the subsequent plotting of principal stress trajectories in key areas to the orthotic shell. These trajectories were then used to guide structural modification aimed at improving the functional properties of the orthosis.
Now, I will discuss the results obtained from computational examinations of an orthosis under loading conditions based on previous FEM studies. A 36 Newton load labeled as F1 was applied to the numerical model to simulate physiological loading conditions. An additional force F2 of 0.1 Newton was also applied. Polypropylene with Young's modulus E of 1500 megapascals and a Poisson's ratio V of 0.3 was chosen as the shell material. The accuracy of this model was validated using electronic speckle pattern interferometry, or ESPI, on a test bench for the original corset. The figure here presents the von Mises stress distribution, indicating that most stress values in the orthosis remained below 6.5 megapascals, except in small surface areas where the load and supports were applied. Since the stress values remain below the material's critical limits, it can be implied that the orthosis can withstand the applied loads and provide the required corrective support without risk of material failure or excessive deformation. It also shows that the numerical model's predictions align with known material properties and experimental data, confirming the accuracy and reliability of the finite element analysis FEA. However, understanding that the orthosis's functional mechanics requires more than just identifying high stress areas, which is where the next slide comes in. The figure here maps the primary stress vectors, specifically focusing on the greatest tensile stresses, or sigma 1. The pathways of these stresses were plotted with splines, starting and ending near the points of applied external pressure. Numerical analysis of these stress trajectories suggests that specific regions of the shell contribute significantly to the brace's corrective function, while other areas primarily provide stability. These supporting areas could potentially be omitted without significantly affecting the shell's overall rigidity.
Several factors can lead to the failure of scoliosis braces. First, in statics mechanics, a poor understanding of forces and material behavior can reduce effectiveness. Imbalanced forces often cause discomfort, tissue irritation, and misalignment. Next, anatomical variations pose challenges, as each patient's unique spine and tissue properties make generic designs unreliable. Areas near bony prominences are especially vulnerable to excessive pressure. And the next one is dynamic factors like movement and growth and further complicate matters by altering force distribution, making static designs less effective over time. And finally, validation issues arise from limited real-world testing and a lack of feedback between simulations and clinical results, leading to ineffective treatment outcomes.
To overcome existing challenges that was stated before, scoliosis braces should be designed using advanced biomechanical simulations that incorporate patient-specific data, account for dynamic changes, and are validated with clinical outcomes. A reliable finite element method, FEM model, can provide accurate biomechanical force modeling, leading to a better brace optimization and effectiveness. FEM models help identify critical load-bearing areas within the orthosis, optimizing its design and ensuring proper spinal correction. Researchers have conducted a FEM analysis of a Boston brace, determining von Mises stress distributions and plotting major stress trajectories to highlight key key force pathways in the three-point pressure systems. Generic scoliosis braces like the Boston brace typically use a three-point pressure system to prevent curve progression. However, stiff, custom-designed 3D braces combined with tailored rehabilitation programs can better address individual differences. Studies have shown that custom braces can not only halt curve progression, but also reduce the KIB angle. For instance, a study reported a case where an overcorrective custom brace improved spinal balance and vertebral rotation. Another study demonstrated the effectiveness of custom-molded symmetric force control brace. In both case studies, it was proven to effectively stop curve progression, reduce KIB angle, and improve posture in adolescent patients.
Our experiment relies on several key assumptions. First, we assume that the brace is new and undamaged, ensuring uniform stress and strain. Second, force equilibrium is maintained, with all forces balanced to prevent uneven stress. And the third one, the brace is properly fitted, allowing even force distribution across the spine. We also assume minimal measurement errors, which won't significantly impact the results. And additionally, there are no external forces like wind or motion disrupting the system. And finally, this assumption simplifies the experiment, focusing on balanced forces, stress, and strain for effective spinal correction.
As a conclusion for this video is, scoliosis braces are a practical example of how we can apply biomedical knowledge to solve a real-world problem. By analyzing these braces, we measure their dimension, identify forces acting on them, and solve related problems through calculation. Braces are designed to counteract abnormal spinal curvature by applying targeted corrective forces, ensuring the spine remains aligned as the patient grows. The proper application of stress and strain is key to their effectiveness. It prevents further curvature progression by distributing forces evenly while maintaining patient comfort. In this case, the customization is critical, as an improperly designed brace can cause discomfort and reduce its therapeutic impact towards patient spinal curvature. This assignment also achieves two learning outcomes, which is first, determining the forces through free body diagram and calculating stress and strain to ensure braces are effective. In our personal opinion, we believe that future research can explore adaptive materials and refine design to further improve the scoliosis braces efficiently. That's all from our group. Thank you.